Okay, welcome everyone. Good morning to some, good evening to others. And yeah, I feel that we got a diversity here. So my name is Evgenia Bragina. I am a conservation director for WCS Russia, and I supervise wildlife conservation society's activities in Russia. I got my PhD a long time ago in Russia with cranes. Since then, I worked with a bunch of species, including Amur tiger and some other carnivores. But my main goal today is to introduce our speaker, which is Scott Waller. And I met Scott in 2018 when he showed up in our office at Russian Far East. The beautiful full day, and I remember Scott was smiling and very enthusiastic, eager to work, and immediately joined our field work there. And if you work in small Asian villages as we do, you know that it's a community which is not necessarily easy to join, especially if you come from another country, if you speak different language, if you grow up speaking different language. Scott navigated these challenges perfectly. He came speaking Russian language, notoriously hard to learn. He knew a lot about the system very well, and he was fresh out of college. However, he already back then wasn't even 25. He already had several years of experience working with large carnivores, with black bears and grizzly bears in Montana. And so when he started working for us, it was clear that he wasn't just a tech. He was observant. He was an ecologist. He was constantly thinking about ecosystem and what are the challenges these mountains face, and so on. And so, of course, a couple of years later, after working for us and living in the Russian Far East, this brought Scott to grad school. And so he started his master's in University of Montana, and that's something he will be talking about today in detail. So I'm not gonna talk about it a lot. But no need to say this work was very, very successfully completed, and now Scott working for us, for Wildlife Conservation Society, as a grant manager, which is, one would think is boring because you always have to write reports and proposals and so on. However, Scott, does it very easily, Yeah, here, here's a report, here's a proposal, very, very nice. And that's been a lot of fun to work with him. So two things strike me about Scott. He always produces new ideas. Just recently we talked, and I asked Scott, so where did you come up with this? Well, I attended this class and I was thinking, and so that makes sense. I'm like, cool. When you find time to produce, to start new things, even being super busy with your main job, it's great. And also, he's always smiling, and he's always nice to people. So we use, between us, we use him as an example. Like someone as nice as Scott. So with that, I won't keep you any longer. I think floor is all yours, Scott, and you should start.
All right, thank you. That was a very, very nice introduction. Thank you, Zhenya. And I want to thank Zhenya because she's in Wisconsin and it's 9 p.m. there, so it's late, yet she's still finding time to give a wonderful. I would maybe have a little more grumpy introduction because I'm making you be here so late at night. But thanks a lot, Zhenya. Okay, I'm gonna go ahead and share my screen, and can you confirm that you can see it?
Yes.
Yes.
Okay, perfect. All right, let's dive in. So as you all likely read in the announcement, right, I'm presenting to you, this is really the title of my thesis, like Zhenya said, at the University of Montana. So it's looking at Cameras or camus. So, and camus is the Russian word for the skins you put on the bottom of your skis to ski around. Um, so essentially comparing snow track surveys and camera traps to monitor unmarked wildlife populations in the Russian Far East. So Zhenya gave a really nice reintroduction. I'll give a little more background about myself. So I was born and raised in Northwest Montana. That's on the border with Canada in the northwest part of the United States in the Rocky Mountains. I was lucky to grow up the son of two wildlife biologists. So grew up skiing around, looking at tracks of wildlife, helping my parents with really interesting research, and was able to turn that passion initially into actual work. I started working for Montana Fish, Wildlife, and Parks as a technician, researching, basically trapping grizzly bears, trying to put GPS collars on females to look at their annual survival and recruitment of cubs every year. So it was an amazing, amazing job. Got some really great field experience. I did my undergrad at Middlebury College in Vermont and studied Russian language there, and just absolutely fell in love with it. So I was looking for ways to intersect those two things. And naturally, that took me to the WCS Russia program. And one thing led to another. I started as a volunteer, then did a master's project there, which was super interesting and which I'll talk about. And now I'm still working for them, so I can't seem to keep away. I also wanted to say this picture, that's my wife and I on horseback. I just got married a few months ago. So shout out to my wife Helena. I'm a very happy man as of late. So just a little bit about myself. So let's dive into the talk. This is really about trying to figure out population density of wildlife. And I think it's fair to say that population density is really the ultimate metric, right? It allows us to compare population size between sites that you can't necessarily do if you're only looking at abundance, and you can compare populations. It allows you to evaluate trends over time, and it allows you to evaluate the success of different conservation interventions. Here's a figure I pulled from Suryan and others in 2021, a paper about snow leopards and the relationship between snow leopards and prey density. And so thanks to these density estimates, we're able to kind of piece apart these different ecological relationships, things like relationships between prey densities and big cat densities like snow leopards. In our own study area in Russia, this is some unpublished data, but it's a really fascinating data set on Amur leopard recovery in the southwest part of the Far East. And thanks to our spatial capture recapture monitoring of Amur leopard density, we're seeing that our conservation interventions, which has been a lot of like greater efforts on law enforcement thanks to Land of the Leopard National Park, we've seen almost a tripling in Amur leopard density over a period of almost 10 years. It's an unbelievable recovery, right? And things like population density allow us to detect that trend and see that our conservation interventions of more law enforcement are paying dividends. Now, you'd think this would be a pretty hard thing to do with elusive and low density and cryptic species like Amur tigers or snow leopards. But it's actually, we figured it out pretty well over the last 10 years, thanks to spatially explicit capture recapture and the fact that these animals have unique markings that allow us to tell one big cat from another. I imagine the people of you who are actually doing this I've actually never used extract compare, but I've seen pictures of it and I've watched people use it. So pretty awesome program, right? Where you get to separate individuals from one another. And then because we know individual animals and we can tell them apart, we can apply the principles of capture recapture. What do you do when an animal looks like this, right? They all kind of look the same, maybe not so confused all the time, but we're certainly confused. And this is a lot harder because we can't tell individuals apart and we can't necessarily apply those capture recapture principles to estimate population density for prey. And beyond, the prey are important to monitor because a lot of times they're local communities rely on them for food. I grew up in Northwest Montana hunting elk and deer, so obviously knowing how many deer and elk you have is important for determining how many hunting tags you can distribute. But specifically in the big context, or in the big cat context, this is the snow leopard network. Knowing prey densities again, help us understand those predator-prey relationships, like that figure I showed earlier. They allow us to evaluate whether prey are limiting big cat recovery. As an example, like if you consider you do an a spatial capture recapture study and get an estimate of maybe 0.2 tigers per 100 square kilometers. But if you do a concurrent study of prey density, because of that relationship between prey density and tiger density, you can predict what the carrying capacity would be if prey were the only limiting factor. And maybe your prey carrying capacity is actually like 1 or 1.5 tigers per 100 square kilometers. So that can help you kind of piece apart what are the main threats and what are the limiting factors for tiger recovery in that landscape. Lastly, I'll say that prey densities can be really useful for assessing the suitability of a site for reintroductions. Of course, again, you want to know how many cats you can fit in a forest, and that's really going to depend on how many deer and elk and wild boar you have. So getting estimates of prey density, and then especially converting those to prey biomass, kilograms per square kilometer, that is going to be really useful and allow you to make informed decisions. In Russia, biologists have used snow track surveys for really almost a century to get estimates of unmarked wildlife population size and density. And in the Russian Far East, they use this for red deer, wild boar, sika deer, and roe deer population size. It's a pretty incredible data sets out there across Russia in different reserves. In Sokote and Lean Reserve, where we're going to spend some time, where our work was, they have 70 years of data of maybe almost 80 years of continuous monitoring with snow track surveys. It's a pretty incredible thing. The unfortunate thing is in many parts of Russia, because of climate change, recent reports by the IPCC are showing that mid-latitudes, a lot of Russia, are seeing more variable winters and especially snow loss. So in our study area in the Russian Far East, especially along the coast, there are places that used to rely on snow track surveys to monitor their ungulates, but suddenly they're not getting snow reliably every year anymore. Or maybe they'll get one big snowfall, but the next day it's 10 degrees Celsius, and so all your snow is melting, and it's impossible to tell the age of the track. So as a result, a lot of managers are in need of a different approach, of a different method, aside from snow track surveys. Another important thing to think about is past work has identified convenience sampling as a potentially major issue for snow track surveys. A lot of times, as far as I understand, reserves will only survey along trails or river bottoms, where it's a lot more efficient to cover ground along a road, right, as opposed to trying to bushwhack through the side of a mountain. But as we're going to see, the snow track survey method really relies heavily on representatively sampling your landscape. So as an alternative method, camera traps seem promising. For one, and especially in the tiger conservation context, a lot of these reserve managers, different conservation groups are already using camera traps to monitor tigers. There's been several new models that I'll introduce you to in the last 15 years that have specifically designed not just to estimate abundance, but specifically density. And the number of studies testing these methods is growing. There's more and more support showing that they can be effective and unbiased, reliable, but none of them really have been published so far specifically in a tiger prey system. So that takes us to our two research questions. The first is, can we use cameras as a practical tool to monitor densities of large ungulate prey? And specifically, do they give us estimates that are similar to snow track surveys? The follow-up question to that, though, is we have to think carefully about how we're leading those snow track surveys. And our question is, do conventional snow track surveys, and I'll say conventional meaning along roads and trails and river bottoms, do those survey routes differ from snow track survey estimates that are based on actual representative surveys? So that's where you're skiing across mountains, across different aspects, different slopes, different forest types. So to get after these research questions, we went to the Russian Far East. Here's a nice map of global tiger range. Look, there's a lot of colors going on here, but just look at the orange colors. That's their current distribution as best as we can tell. So I'm going to show you some pretty amazing pictures of Suitability Reserve, which is in the middle part of the Far East, middle part of the southern Far East. It's on the coast of the East Sea, or the Sea of Japan. You've got beautiful forests of Mongolian oak, and then steep cliffs going straight down to the ocean. And what's another really unique part, and I'll say these Mongolian oak produce acorns that are a very important food source for the ungulates that we're going to be looking at today. If you go into the Suitability Mountains, basically west, further inland, you pretty quickly transition into dark forests of spruce and fir, some beautiful old growth riparian forests along these big rivers. And that's, I haven't spent a lot of time in these places, but that, to me, that's the true feeling of the taiga, right, in Russia. And this is a beautiful photo of the Iman River, just west of the Suitability Reserve. Our key players today that we're studying are wild boar, sika deer, roe deer, and red deer. These are the 4 main prey species of the Amur tiger in the central Suitability Mountains, making up, 80–90% of their diet. I want to give you a little bit of statistical knowledge about how these models work, and we're going to start with the FMP. This stands for Formozov-Malyushev-Pereleshin. So naturally, at least the English-speaking world, we shortened it to FMP. You can also call it just the Formozov method. But the principles are very straightforward. The idea is that we can estimate the density of a population if we know the number of fresh tracks that we encounter along any ski transect, and if we know the study animal's daily travel distance. Here's the equation for it. It's very straightforward. Basically, we can estimate density of a population. Again, if we count the number of fresh track intersections, and these are less than 20, they have to be less than 24 hours old. If we know that daily travel distance estimate, if we record the total kilometers of surveys that we ski or walk or snowmobile, and then we multiply that by the probability, basically pi over 2, this constant, which it's a very simple constant, but it's basically the probability of encountering a fresh animal track based on that animal's daily travel distance and integrated over all possible angles of intersection with your transect. So I can share some interesting papers if you'd like that dive into this. There's a lot of calculus and integrals that go into just this simple pi over 2. It's pretty amazing. And of course, we can't just rely on a point estimate. We need some sort of estimate of sampling variance. So we just use bootstrap. We bootstrap across your different transects to get a mean and a standard error. Our camera trap methods are rooted in a lot of the same ideas, but of course it's a different way to sample the landscape. So we're going to be talking about this class of models that we call viewshed density estimators. And that's because they estimate the density of animals within the collective viewsheds of your cameras. And by viewshed, I basically just mean that area in front of your camera where animals can be detected. It's a very complicated term, but just bear with me. So, and again, they're called viewshed density estimators because we're essentially counting the animals within that known area, the literal square meters in front of your cameras, and then extrapolating that estimate across your whole study area. So that's why the assumption of representative sampling is so important, and we'll get to that in a second. There's 5 models that are the most important and are rather most popular and most applied. The first is the random encounter model, or RAM, which you all have probably heard of or even used yourselves. There's also camera trap distance sampling, which is a little newer. The random encounter and staying time, or REST model. Then the space to event and time to event models, the STE and TTE. I'm going to very quickly try to explain these to you, and I'm happy to go back to these slides if you'd like or share these. But I came up with these little schematics that hopefully kind of visually represent how they're different. So the random encounter model, you're basically counting detections of animals within your viewshed, and the dotted line here is that how far they're traveling in a day, right? So those are the pieces of information, the pieces of information that you need. The camera trap and distance sampling model, you don't need estimates of animal movement rate actually, because you take snapshot moments, typically every 2–3 seconds. You're taking snapshots across the images that you collected. And then when there's a detection of an animal, you measure the distance to that animal. And this is actually a type of point transect distance sampling, which you might be familiar with. Your camera is your point, and basically this model was developed with the pretty nifty idea or realization that animals that are further away from the camera have a smaller chance of being detected by your camera. Because remember, these are working with passive infrared sensors, and animals that are further away, less of that radiation is going to be picked up by the camera, and so you've got a smaller capture probability. So then you get these classic distance sampling curves, and you can estimate your detection probability that way. The random encounter and staying time model is very similar to the random encounter model, but instead of looking at the animal's daily travel distance, which you can either estimate separately with this camera data or you use some other independent estimate. The REST model, you actually count the amount of the amount of time that your animal spends within a very small area in front of your camera where you're assuming perfect detection. The final two are the space to event and time to event, which are related. The space to event, basically, if you imagine this blue polygon as your study area, and you have these 9 cameras across your study area, you have basically at each occasion, so at each snapshot instant in time, let's say it's 12 o'clock midnight, you randomly sample across all of your cameras in your study area until you get a detection of an animal. If you don't have any detections, as you know, all these animal, like if you imagine the green camera as a detection, there were no detections in this first occasion, so you do what's called right censoring. Let's say 15 minutes later, you have your second occasion. So once again, you randomly sample across all your cameras, and it'll be a different order of camera, right? Because you're randomly selecting, and you randomly sample until you get a detection. Once again, there were no detections, so you right censor and you move to the next occasion. Finally, let's say you sample randomly camera 1, 2, at that third camera, there's an animal detected. So that is your space to event at that occasion, right? You're literally summing up the space, that viewshed area in front of your camera. Let's say it's 10 square meters. You say 10, 20, 30 meters. At that occasion, it was 30 meters until I detected an animal. So hopefully that kind of helps you realize why it's called the space until event, right? It's literally the square meters or square kilometers, whatever, until a detection of an animal. Lastly, the time to event, it's related to the space to event. I usually think about it as you're essentially collapsing that to each individual camera, and you sum the space at until a detection event, but instead of across space at one occasion, you're actually sampling that same camera at smaller intervals of time. So you can imagine you have three cameras here. Maybe the first camera, maybe your sampling period was like 20 seconds. Right to that second sampling period, you got a detection of an animal. It's like, okay, that meant it was only, 10, 20 square meters until my detection. At the other camera, however, you had to sample 8 cameras until your detection. So that was 80 square meters until your detection. So it's just a different way to essentially build a Poisson distribution, or excuse me, an exponential distribution from which you can estimate your rate parameter of density. That was a very fast, very quick and dirty overview of these methods. If you're interested, I very much encourage you to go back to the original citations. I'm happy to share those with you. So in our study, we only looked at 3 of these just because honestly, because I was a student and new to this and I could only handle so much. And I didn't even know about these 2 models when I started. So we looked at the random encounter model and then the space to event and time to event models. Really quickly, I don't want to get too much in the weeds with the assumptions, but I do want to highlight several important assumptions that are consistent across these models, and that is especially the assumption of representative sampling. Recall that these are viewshed density estimators, and you're assuming the density that you estimate in the viewsheds of your cameras can be extrapolated across your entire study area, that area you're interested in. So it's very important that your cameras represent your study area, and that's why we have to use things like random sampling or systematic sampling. It's very important also that animals are moving independently of where you place your cameras. So you can't place them on roads or trails, things that might attract or repel animals. And for the space to event model, you really need to instantaneously sample at each occasion. Remember, that's the one where you're sampling randomly across your cameras at snapshot occasions. It has to be 1 second. Otherwise, it'll introduce a positive bias. Like if you start saying, well, at this snapshot, I'm going to include all detections in like a 10-second or a 30-second window. That's not very long, but actually, this needs to be researched more, but you basically start animal movement rates start to become important as your sampling window becomes bigger. Lastly, for the SnowTrack FMP method, but also the random encounter and time to event, you do need accurate estimates of animal movement. And that's a pretty costly parameter. You can do it from camera traps, but it's a lot more time. And we ended up just using estimates from the literature, basically a study 10 years prior in the same area. So we thought that was a safe assumption because it was the same species, same study area, same period of time, of the winter. So that actually ended up working out pretty well for us, but that's an important thing to keep in mind. Okay, that was a lot of statistical information about these models and their assumptions. So let's go back to actually trying to test these and see how they worked in the field. So recall where we are. We're in East Asia, Northeast Asia. Here's the Russian Federation. People's Republic of China is just across the border. We're north of the Korean Peninsula and along the East Sea between Japan and Russia. We were working specifically within the Sokotelin biosphere Zapovednik. A lot of you are probably familiar with Zapovedniki. But if you're not, they're one of the most strict forms of nature protection in the world. It's pretty incredible. But basically, there's very limited tourism, and you have to have permission from the reserve director or someone from the reserve. And typically, you need to be accompanied by reserve staff to whether you're doing research or something there. So, and this is the southern study area here. That's about a 500 square kilometer area that we did our research. Zoomed in here, that's that same southern study area. The light blue dots are the random cameras we deployed in our last winter, just kind of showing you, the extent of our camera trapping. The blue lines, those are the SnowTrack surveys that we did that we're calling our random track surveys. They weren't truly random, but we drew them in consultation with the reserve to try to adequately represent the variation in terrain, elevation, aspect, forest type, to try to represent this study area while still also being actually feasible to do, right? Because if you might try to go in this is very, very remote area. So there are some practical limitations. The last thing to point out here, the red dotted lines, those are the roads and trails that the reserve typically uses in their annual surveys, what we're calling the conventional routes. This was an absolutely amazing project, and I'm really grateful for WCS for supporting it and all the friends I made along the way who helped me with the field work. It's an absolutely beautiful part of the world. This is looking out east, from close to we had just summited this one peak, and then we're coming down, looking east at the ocean there. It took a lot. People were really good spirits. I think typically when people camera trap, they want to go and try to maximize detections of animals, but I went there and basically tried to convince them that it was very important that we use the Russian word is sluchayny. And I think on the field staff hate that word now because it meant they had to climb these ridiculous, steep, slick hills. I know a lot of you are working in snow leopard habitat, so this is nothing, right? But it's still hard work when it's basically you're walking on ice and trying to get to the top of this hill to put your camera trap. I will say that gets you to parts of the reserve that people have not been for many, many years, and you get to see some really fascinating and beautiful places. Here's a really nice photo I was able to take of tiger tracks across a log, crossing a creek, and then just kind of walking along the coast as we had spent a couple days putting cameras out, and we were headed back. Just beautiful views. Not always necessarily a beautiful view. A little hard to tell from these photos, but there was a lot of bushwhacking, a lot of going through deadfall that was over your head. But everyone you know, stayed positive and we got the work done, and it was a really great time. I do want to give a shout out to the different the WCS staff in Russia, but also the reserve staff and the local hunters who all came and helped us with our snow track surveys. We did a kind of a big flash effort, did a bunch of skiing all those routes, and it was a lot of fun and a great team. All right, so what did we find? We did 3 years of study in early 2020, the winter of 2020 to 21, and then the following winter 2021 to 22. We put about 36 cameras out the first year. Rather, these are the number of cameras that actually functioned. We usually had about 5 or 6 cameras that didn't work for one reason or another. So we had 36 functioning cameras the first year, 38 the second year, and 45 the following year. We used a 60-day period to analyze the camera data. For the snow track surveys, we had about 100, I think it was around 120 kilometers each year for the conventional routes, skiing those same routes. But the first year, our random routes, we did about 70 kilometers. It was very challenging weather conditions, so we had to cancel and recancel and reschedule our routes a lot because of bad tracking conditions. The second year, we did about 100 kilometers more, so 170 kilometers total. That was our last year. And the second year, unfortunately, because of COVID, we weren't able to organize any random routes that year. So a couple things I want to highlight in this figure. There's a lot going on, but basically each year, those are our at the bottom here, you see the different years. That's our x-axis, and then the y-axis is the different density estimates. We've got 4 panels each for the 4 prey species that we're looking at. Then lastly, the blue colors are the snow track based surveys, both the conventional routes and then the randomized routes. And then the different shapes are the different camera trap models in orange. So I think one thing to notice is we've got general agreement across the models, I would say. The third year was a little less agreement. Especially the first season for wild boar, there was pretty consistent or a pretty considerable disagreement between snow track surveys and cameras. This big drop in wild boar density, that is not a fluke. That was because African swine fever hit our study area between these 2 years of surveying. So it was a 95% decline in population density, pretty dramatic and pretty concerning, really, for tiger conservation. And another way to, we don't know truth here, right? So this is pretty hard to evaluate the different methods. But one thing we tried to do is we knew that our conventional routes were meeting the assumptions of the model with the snow track surveys. So we were the second best thing that we could do without knowing the truth is look at what models were agreeing the best between the conventional routes and then the camera-based models. The first thing to note, so this is just basically the same information shown a little differently. On the x-axis, now we have the random FMP density estimates, and the colors are the 2 years. Unfortunately, again, we didn't have that middle year because of COVID, but we still have 2 years. So the black and orange here. The different shapes are the different species, and then the different panels this time are the different models. The solid line, that indicates if an estimate is on that solid line, that means that the random FMP, the random snow track estimate and the camera-based estimate, they're aligning perfectly. The dashed line is the actual slope of the relationship of estimates for that model, for that camera-based model and the random FMP. We did also look at the relationship between the random track survey routes and the FMP conventional estimates. So this is an important first thing. We found a consistent positive bias. See how that dashed line is consistently above the solid line? That means across the board, species, or rather on average, the conventional survey routes lead to a positive bias. The other 3 methods, notice that their intercept is also at 0. So that means you've got a 0, or how do I say this? You don't have any relative bias, but you've got a positive slope because estimates for species that are higher density seem to be less consistent. And I interpret that as basically the species that are more abundant are also the species that are generally more sociable and live in herds. So they're a little more they're a little more difficult to estimate with these models. And I also want to point out, look at the black color. Our first year, we had really good alignment for 3 of our species. It was just wild boar that I think is really kind of, it's an outlier, and it is kind of positively skewing this dashed line. And I think the main reason for that is there were a ton of wild boar in our study area that first year before African swine fever. And it's really hard to accurately count the number of individuals when you've come across a bunch of tracks, right, of a big herd. So we probably undercounted the number of wild boar in our track surveys. That is my best guess of what's going on there. Lastly, we converted them to biomass using conventional methods based in the literature, where basically you just take your prey density estimates, your point estimates, ignoring the uncertainty, and you multiply it by typically the average female body weight of your prey species. And some papers have then additionally multiplied that by 75% to account for like decomposition and scavengers and that kind of thing. But we did this because, again, we're really interested in the tiger conservation lens. And this is where it's most useful for tiger conservation, is looking not just on prey density, but actually prey biomass. And the important thing here is there's a lot of variation across your methods. In the first year, it was a little better with the camera models, but the following years, you've got a lot of variation. And again, the important thing here is that the conventional methods that we use to estimate biomass, just multiplying your point estimate, it ignores your estimates of variance and estimates that might be not statistically different because they've got overlapping confidence intervals. They might lead to a pretty big difference in your prey biomass. So just look at this third year, 2021 to 22. Maybe practice, if they were to use the space to event model, they're going to get only 100 kilograms of prey biomass per square kilometer. That's going to be a way smaller predicted carrying capacity of tigers than if they had applied the time to event model, where you've got almost 600 kilograms, right? That is the most extreme example that we have here. But I think it's important, right? We need to be really careful, and I think it points to the need that we need to develop some new methods that are better at estimating prey biomass. So let's run through some of the key takeaways. The first one is that we really, and I can't emphasize this enough, you need to have a representative sample of your landscape, both for the snow track surveys and for your camera traps. We saw that in that positive bias between the conventional snow track surveys and your randomized surveys. And then this is actually from my second chapter of my thesis. But basically, I took what I called a complete sample. It was like 5,000 points across my study area, and I sampled different key landscape attributes like elevation, slope, terrain ruggedness, forest type, that kind of thing. And what you see is those 5,000 points, this blue kind of density curve here, it matches really well with our random sample. This is only 45 points compared to 5,000. It doesn't match perfectly, but the shape is almost the same, right? It's very similar, and it's statistically the same. Look instead at if you put cameras only along roads and trails, as is done when you're monitoring tigers, or we even tried going about 150 meters away from that road and trail, trying to get away from the effect of that road, how it might impact animal movement. Those are these two colors skewed far to the left, right? Even if you get off the road, you're still restricted to much smaller elevations. And this is a similar pattern that we saw with all different landscape attributes. So I really want to discourage everyone from applying these viewshed density estimators to your data that you might already be collecting for tigers or even snow leopards, right? And I've highlighted in red the key model assumptions that you're likely to violate. The first one is representative sampling. You're likely not to actually meet that assumption of a Poisson distribution of animals across your landscape. And you're almost certainly not observing animals, or rather your camera traps are not independent of how animals are moving, right? Because almost every animal is attracted to or repelled by that linear feature. So that was one of the main questions, right? It was going into this thesis. It's like, we're already collecting data to monitor tigers. Can we use this data that we get of prey as well? The answer is no, you can't if you're trying to get actual prey density. Another key takeaway, I think, is the challenge of group size. There's different results in the literature. Some people find that herding species, especially wild boar, there's been a lot of camera studies of wild boar. Some studies get very strong agreement between camera-based methods and reference density estimates, but others don't. In our own study, we found some pretty inconsistent results, right? Our first year, we had almost perfect matchup between our snow track survey routes and camera-based methods for Sika deer. It was super exciting. The following year, the camera-based estimates of Sika deer were way higher, and it's just not totally clear why that is. I think this is something that is deserving of more research for a better understanding. I also want to highlight that if you're applying, whether you're applying the snow track-based FMP or you want to use the random encounter and timed event, these estimates are very sensitive to what you use as movement rate. So here's a paper from, I'm sorry, I got the year wrong. This was Kenneth Lunam. He was another student at University of Montana, his 2020 paper. He's showing how estimates of mountain lion or cougar density in Idaho, they're really sensitive to that estimate of movement rate. And this is for the random encounter and time to event model. So that's a big consideration for the FMP, REM, and time to event. For the space to event, you don't need animal movement rate, but estimates are still very sensitive to a different parameter, and that's that sampling window duration, right? I want to emphasize that you really need to use instantaneous sampling if you're going to apply the space to event. Otherwise, you see across all these different study areas and species, it's as you increase that sampling window, as you're not sampling just at 1 second, you're including detections of 10 seconds, 20 seconds, the 30-second window. That density estimate is just linearly increases. And this is another thing to think about. We ended up, for our second and third years, we used Panthera camera traps that were specifically designed for for carnivore surveys, but as a result, they didn't have very consistent sampling when they would snap photos. There might be a 2, 3, or 4-second delay between photos. So that actually meant there would be an animal in front of the camera, just no photo. And so when we tried to snapshot sample that camera, we ended up with a negative bias. So I think that was a result of some of our low estimates from the space to event. Lastly, as I kind of showed in detail, converting these estimates of density to biomass can be pretty problematic. And I really think that there's a need and opportunities to develop better methods to convert prey density to biomass and just ways to estimate prey biomass in Atlanta landscape. Now, I want to leave us with considerations for snow leopard range, right? Because again, this is the snow leopard network. I'm really appreciative of being able to share our research in a tiger context and think about what this might mean in a snow leopard range. So the first thing that comes to my mind is, oh my God, how hard is random sampling in the landscapes that you guys work in? That's not to say it can't be done. I did find a paper by Pal et al. In 2021 in the Western Himalaya of India. They used camera trap distance sampling, which is still a viewshed density estimator, right? Same principles, same assumptions. They used camera trap distance sampling to estimate densities of some mountain ungulates. And this picture is a screenshot from their paper. So I'm really curious to hear from you all if you think these methods that we found, we see a lot of potential in, but some main challenges. But challenges that you can account for and you could plan for, and then ultimately get hopefully accurate estimates of prey densities. I'll leave you with this adorable photo of a mom and her cub playing in the Russian Far East. And thank you very much. Thank you again, Snow Leopard Network, for this opportunity to present. And I'm excited to hear your thoughts and discuss this with you. Maybe I might keep the sharing on actually so that I can go back to slides if people request.
Yeah, there is a question for you, Scott. Thank you so much for this presentation. A lot of information, but very exciting. The question is, you said you used the previous estimate of animal movement. Does it ever become a concern that animal behavior or daily travel distance would have changed once snow cover diminished?
Yeah, I think that's a fantastic question. Actually, that was the same question of one of the reviewers of the manuscript I'm working on. I think the reality is we didn't have the resources to try to estimate animal distance ourselves, and that was the best we could do. But absolutely, and then that could account for some of the variation that we saw in our estimates as well. I think the gold standard should be estimate animal movement during the time that you're studying. And there are some pretty well developed methods now where you can use camera trap data to estimate your animal movement rate as well. Um, and absolutely, things like even within our study area, that's really dependent on acorns and pine nuts. We've got GPS data from wild boar showing wild boar can travel 100 kilometers in a period of a week to go from the coast in across the mountains into the pine forest to look for pine nuts. So they might be doing that one year, but the following year they might not go anywhere because it's a really good acorn year. So I think that's a really good point and certainly a limitation of our results here.
Thank you. Another question, actually, that was the previous one. I missed. For group sizes estimates, have you used sighting quantities on the cameras? Did you use field observations?
You know, we actually didn't use the observed group size. And some past studies I know, especially for the random encounter model, they do count the number of animals in your cam that you can see in your camera. The problem, however, like I'll point out with this, our effective detection distances, like the detection distance that we use, and I didn't have time to talk about this, but this is a very important parameter. It's you should never just use the manufacturer's estimate of that detection radius. You need to use things, it's called the effective detection distance, where you're basically using distance sampling to measure that, basically that distance at which animals are seen. Like in this picture, you can see about almost 10 Sika deer behind this main Sika deer. But if that Sika deer in the front weren't there, potentially none of these animals would have been detected. So I think and this is something that needs to be understood better and investigated. But I think it's a fair argument that as long as you're measuring the distance to that first animal in front of the camera, that is the detection that matters, and you don't need to count these number of animals. And actually, I can't remember the names off the top of my head, but I know like there's an example where they use the random encounter model to study lion density in Africa, and they only got good estimates if they used individual detections and did not count the group. But yeah, it's a good point. It's a tough thing to think about.
Yeah, thank you. So here's your favorite question. How did the resource demands, time, labor, and financial costs of using camera traps compare to those required for the FMP method?
Yeah, great question. The FMP method takes a lot fewer resources. It's of course a lot more challenging because you're at the whims of the weather, right? You're planning around the weather, and that's never a good thing to have to do. But if you've got the environment and the conditions where you can do snow tracking, I do think 100% it is more economical and more efficient. Let's see if I can remember the statistics. We ended up our last year, we walked and skied about 160 kilometers off trail for our surveys. But for deploying and then retrieving the cameras that we deployed in that same study area our last year, it was almost 500 kilometers. So it was nearly triple the effort that it took, right? You're bushwhacking, you're going off trail. Not only you have to put those cameras out and then you have to go back and get them, right? So it's at least twice as much effort, but for us, it actually ended up being 3 times the amount of work. Then once you have the data, at least the way that we collected it, they're basically we we made these booklets with glue and cut up graph paper. And you collect the booklets from the people who are doing the surveys, and then you just transfer it into Excel. And it took me 1 day to do that across about 19 survey routes. Whereas with camera trapping data, I know that there are new automated methods with AI, machine learning that are exciting and pretty awesome. They're not quite good enough yet that you can't just rely on them on completely. You have to do manual sorting, and a lot of times, especially when you're dealing with 50 plus cameras, you've got hundreds of thousands of photos to sort through. So the time investment of processing the data is a lot more for the camera traps as well.
Thank
That's a
you.
great question. Thanks.
There are a lot of thank you, Scott. Great talk, Scott. A lot of compliments. So,
No, thank you.
which I think are very well deserved. And yeah, author of the question, thanking you. And it looks like she came up with a new question. I apologize, I'm not saying the names just because I'm really afraid to mispronounce the names of everyone who's participating in the discussion. How did researchers convert density estimates to prey biomass? And what were the main assumptions involved in this conversion?
Yeah, that's a great question too. So typically, so what we did is we used estimates of prey average. I think we used average female body weight, live body weight. It's in this Soviet. I think it's Bromley and Kucherenko from like 1987 or something like that. They have some body weight estimates, and we used female weights because the idea is that the female weight kind of averages between the younger and smaller animals and the older males. And it's a lot of hand waving, and I think because biomass is so useful, we should try to develop better methods. There's a paper, a pretty seminal paper by Ulas Karanth and Sundquist in 1992. They did a better job. They actually, and I think actually George Schaller in his 1967 book did something similar. They take the average body weights, but by sex and by age class, and they kind of adjust. They use their observations of these different sexes and age classes and adjust body weight that way. But no one has really done that. People either use the weights that are reported, and like the tiger studies in India that look at prey biomass. A lot of them rely on that Karanth and Sundquist paper, or they do the simpler method that we use, where you multiply by female body weight and then potentially additionally multiply by 75% to account for decomposition and scavengers. So, especially with camera trap data, we've got images of the sex and age class, and a lot of the times you can tell in the photo what you're looking at, right? So, I think there's a huge opportunity to use all these data sets and actually develop more robust methods that apply to the study in question, right? As opposed to drawing on the literature.
Thank you. The author of the question says, how interesting. So, were there any communities of human activity anywhere?
Yes, so not really in our study area actually, because recall that this is a Zapovednik, so entry is tightly controlled and restricted. So where we did our surveys, it was all remote, wild. The animals might be, because the reserve is bordered by private hunting concessions. Certainly some of the animals were used to being hunted. But there's also the village that we stayed in, that we were based. It's called Ternay. It's right near the reserve, the Zapovednik border. So that was the nearest community. It's a pretty small community. I think about 3,000 people, more or less. I apologize for not having a sources slide at the very end. I'll send Raki. I don't know if there's like a good, if I should just email them to you, that the couple citations I've referenced so far. But that's certainly something I can do.
Did you find any sign of illegal activities, people ask?
We actually didn't. No, I would say the most the biggest thing that we saw was actually dog tracks in the snow. I think that's can be a pretty big problem in the reserve, is just stray dogs harassing wildlife. And especially closer to Ternay, we did see lots of dog tracks, but that's not illegal activity, right? That's just human impact.
And Raki says yes, please send
Great, yeah, I will.
citations. Yeah. Thank you again, Scott, and thanks to everyone who was listening today, asking questions and learning about this quite amusing, very interesting research.
Thank you, everyone. Really happy to share our research with you. And I wanted to say we're working on final revisions in the journal Ecology and Evolution. So hoping for the manuscript with our results to be out, so you can, basically all the same results here. So you can dive back into that. And please don't hesitate to email me if you have any questions that come to mind. Very happy to discuss them, answer your email, or get on a call or anything. So thanks, everyone.
Yeah, people ask you to share the paper when it's ready, Scott.
Yes, certainly. Yeah.
Yeah, you can send it to us as well, Scott, so that we can put it up through the network as well.
Great. Yeah, I'll make a note to make sure to send it to you.
Thank you so much, Jenya and Scott. That was awesome. Amazing.
Thank you so much. It was
Awesome.
a lot of fun it's always fun to share this. So thank you.